So we have the energy state. The lower the energy state of an atom, the more stable an atom is. We've talked about that. So you should know the difference between an excited and a ground state. We can use the transition between the excited and the ground state to learn information about various molecules. And we're going to walk you back through the spectrum. Remember we talked about radio, micro, infrared earlier in this presentation? Now we're going to walk you through some of the ways chemists use the different parts of the spectrum. Now this is radio spectroscopy. So what that is doing is it's using radio waves that are very, very, very low energy to change the state of the nucleus. So you have an atom, let's say if we just make it hydrogen, if you have a lot of energy, the energy is absorbed by the electron and it bumps the electron up like we've talked about. But if you have a very, very low energy, it can actually excite the nucleus and it can actually cause the nucleus to align to a magnetic field, which is really kind of interesting. So if you use very, very, very low energy radio waves, you can excite the nucleus instead of the electrons, and based on how the nucleus interacts with the magnetic field, you can figure out what the nucleus is. So this allows us to count the numbers and locations of the different types of atoms that are present. So here's an example of what you would see. This is what a radio spectroscopy printout looks like. Now you are not going to be expected to interpret this. It's not like I'm going to give you dots with these not here and say, okay, what is the molecule? That is an example of something that you can do in upper level university chemistry or maybe even graduate level chemistry at this point. But just know that because of the interaction between the radio waves and the nucleus, it allows us to identify atoms. Next, we have microwave spectroscopy. Microwave spectroscopy, remember the microwaves are actually slightly higher in energy. So we're no longer looking at how the nucleus becomes excited, but now at this point we're looking at how the molecules rotate relative to one another. So for example, if I were to draw this molecule right here, let's draw it. Let's make it a single bond just to make it easier. So we have this right here. And you should know what this is called, or what the name of this molecule is. And let's go ahead and make it like this. We'll make these chlorines. Okay, this is a derivative of ethane. It would be dichloroethane. But if you were to look at this, you can actually rotate molecules and you can see how they line up to see if the chlorines line up here, opposite of one another, or if they line up on the same side, which is called cis-trans isomerism, which you don't need to know about. But because microwave spectroscopies are slightly higher in energy, you can actually rotate the molecules into different states. And when you rotate them into different states, you can see what the energy difference is, and you can actually see what state the atom is most likely to be in. Once again, I'm not going to give you this and say, hey, what state is the molecule in? But you do need to know the interaction between the radiation and the ability to find some sort of information. Next, you have infrared spectroscopy. Infrared spectroscopy is very, very key in organic chemistry. Organic chemistry is generally the second year of chemistry in a university. If you take the AP test and you test out of the first year of chemistry, it may be your first class at a university level. Now, infrared spectroscopy is a way of being able to, we're not talking about rotating bonds now. At this point, what we're talking about is vibrating the bonds back and forth. So if I have enough energy, remember, these really represent electrons. So the electrons can move one way or they can move the other, like a spring. And so the spring goes back and forth, back and forth, and back and forth, depending on what type of infrared waves that I put on the molecule. And so as a result of that, I can actually stretch the molecules out and I can produce what's called an infrared spectrum. Now the nice thing about an infrared spectrum is all the bonds in a molecule tend to be in the same place. So this right here is bromomethane. And so because it's bromomethane, each one of these peaks would represent a different part of bromomethane. It could be a carbon-hydrogen bond, okay? Or it could be a carbon-bromine bond. And what you would do is you would compare this infrared spectrum to a known series of spectrums, and you would line them up and say, okay, that means these are the functional groups. By functional groups, they mean things that are attached to carbon. Okay, that's all organic chemistry is interested in. So once again, we have three things. We have excited the nucleus to kind of see what nucleuses are there and where they are. We've seen the three-dimensional structure, and now we're already looking at the functional groups that are there. Generally speaking, UV and visible spectroscopy is used to sometimes to ionize, but generally it's used to figure out what the concentration of an unknown is. Now, we will actually do this lab, so we're not going to go too much into it because we're going to do the Beer-Lambert law. But what this will allow you to do is figure out how much of a specific substance is in a solution. Okay, there is something called photoemission spectroscopy, and what it does is it uses high energy UV and X-rays to ionize an atom. So what they do is they say, okay, I have all these UV rays that I'm going to send. Here's the spectrum. I've sent all these UV rays at an atom. What I get left is a hole right there. So this must have been the energy that was required to ionize the atom. And what this is this represents what is also known as we looked at this equation before when we looked at the photoelectric effect. Okay, the energy that an ejected electron has is equal to hv, which you should know is the energy of a wave, or the energy of this wavelength, and then this is the energy that it has. It's called the work constant. It's the amount of energy required to release the electron. De Broglie's dissertation. So far we've talked about electrons as being, light as being a wave or a particle. Well, de Broglie actually suggested in his doctoral dissertation that maybe electrons can be modeled as a wave, because so far electrons have been treated as particles. So what he did is he said, okay, well, I'm gonna pretend, just as kind of a thought experiment, that electrons are actually going to be modeled as a wave. And if they're actually modeled as a wave, he related Planck's constant, and you should be familiar with this term from physics. This represents the momentum. If you haven't taken physics yet, that's okay, it's no big deal. But this is the momentum of a particle. It's the mass times the velocity, and those two are related to each other, give you the wavelength. So this will be the wavelength of an electron. And if you notice it, the wavelength of an electron determines on the mass of an electron, which is constant, and then the velocity of an electron, which changes in its position related to the atom. So if you kind of extend this out, well, let's look at an example first. What is the difference in wavelength for a 2,000 kilogram car traveling at 20 meters per second and an electron traveling at 70,000 meters per second? Now, if you were to look at this, it says we're trying to look at the difference in wavelength. Now, remember, wavelength is equal to h divided by mv. Well, for the first one, I'm looking at a car, which is 2,000 kilograms traveling at 20 meters per second. That one's pretty easy. I would get 6.626 times 10 to the minus 34th. And the wavelength of this particular car ends up being fairly small, because I'm taking Planck's constant and dividing it by 2,000 and multiplied by 20. So the total result would be 6.626 times 10 to the minus 34th divided by 40,000. Really small number. Now, when you look at it for an electron, it's quite a bit different, because if you look at an electron, it's 6.626 times 10, 6.626 times 10 to the minus 34th divided by the velocity, which is much greater, 70,000. People say, oh, well, that's an even bigger number. But when you look at the mass of an electron, 9.11 times 10 to the minus 31st, that is extremely small. It starts to get to the point where you are actually going to have a reasonable wavelength. This is going to be something like times 10 to the minus 40 or something like that. Okay, this is going to start to get into something like 10 to the minus 6th or 10 to the minus 7th, which is interesting because that's actually a wavelength that you can see. So you have to start to look at these sorts of things and say, well, there's no way you could ever see that, and it's really small. What happened as a result of this, whenever de Broglie published this hypothesis, people extended it further. And one of those people, well, first they had to prove it. So they had to prove it, and this was a famous experiment that was done by Davison-Germer. And it's another example of people being able to apply ideas and test them experimentally. So what they did is they actually came up with an electron source. And that's not hard, it's just like electricity going through a wire. So they had electrons, and what they did is they fired electrons at a nickel crystal. This is a crystal. And normally what you would expect to happen is you'd have a bright spot and then it would fade, just like a flashlight. So you would expect to see the same thing whenever you fired solid particles at it. Think of it as Plinko balls, or a ball trying to travel through there. But what they found out instead was there was the same interference pattern they saw with light. You had a bright spot and then it was dark. and then you had a bright spot, and then it was dark. So what this showed is that electrons can interfere with one another. Now, one of the extensions of this, the fact that we can do this, allows for the creation of what we call electron microscopes. What this allows us to do is we can actually convert images, and we can actually take electrons and the wavelength of electrons, and we can actually convert them into visible light. What that allows us to do is that allows us to quote unquote see things that are much, much, much smaller than what is actually possible using visible light. So whenever you're shown a picture of DNA in a cell, that was obtained from an electron microscope, because the DNA itself is so small that you'd never be able to see it using visible light. Okay, that's an example of what it is. Werner Heisenberg extended this idea of de Broglie, and what he came up with was the Heisenberg uncertainty principle. And it came up with this idea that location and momentum cannot be simultaneously known. And the reason why he came up with this is if you take the whole idea of wavelength equals h divided by mv, well, this right here, remember, is the momentum. Momentum is sometimes represented as p. So you have wavelength, you have h, and you have p. Well, if you were to look at this, wavelength, whenever you have a wavelength, there is some uncertainty in exactly where the electron is, if you think about it that way. If you think about the electron as a particle, is it here, or is it here? Or is it here, or is it here? There's some uncertainty in exactly the position of it based on the fact that it has a wavelength. Okay? So since you don't know exactly where it is, that uncertainty gives us what we call the uncertainty principle. Now, this uncertainty principle was mathematically proven to come out to be delta x equals delta x times delta p has to be greater than or equal to h bar over 2. Now, this h bar and this h are related. H is equal to 6.626 times 10 to the negative 34th. H bar is equal to h over 2 pi. Now you say, well, why would they do that? Why would they create a whole new variable and not just put h over 2 pi? The reason why it is this constant right here comes up so much in chemistry when you look at the atom that they decided to give it its own variable, because it just comes up that often that it's better to go ahead and make it its own thing. So now we're going to calculate the minimum uncertainty and position of a proton with the uncertainty and velocity of 1 times 10 to the minus third. So one of the things that we want to talk about is the Heisenberg uncertainty principle generally only applies to electrons and things that are smaller than electrons. And the reason why is you have delta x, delta p, greater than or equal to h bar over 2, which, remember, h bar over 2 is 6.626 times 10 to the minus 34th divided by, at this point, 4 pi. Okay, because this is h over 2 pi, got to add the other to it. This is such an incredibly small number that unless you have very, very, very small values, this will always hold true. If you think about a car has a mass of 2,000 kilograms and a velocity of sometimes 20 meters per second. You have 40,000. So you would take this number and divide it by 40,000, and that'd be uncertainty in position. It's basically zero. So if we plug in an electron, now remember this delta P represents the momentum. So you would say delta X, and then you would say your uncertainty in position and your mass. So here's your your velocity. Your mass is a proton. You would look that up on the table. Has to be greater than or equal to h bar over 2. At this point, you would divide both sides by 1 times 10 to the minus third and 1.672 times 10 to the minus 27th. Okay. At this point, you are starting to once again deal with relatively small numbers. I would have to multiply both sides, and I would have to I'd have to divide both sides by that, and you end up getting a pretty small number. Okay, I'll let you do the math, kind of figure it out what it is, but it ends up being reasonably small. Okay, it's not within anything that's bigger than like 10 to the minus 10th. You have to start to deal with depending on your experiment. So it's one of those things where if you go smaller than a proton, like an electron, this can actually be fairly significant. But once you're talking about protons and atoms, it tends to be to the point where it doesn't really matter. Erwin Schrödinger took the idea that came from de Broglie, and he extended it even further. He took the idea, physics has had a fundamental wave equation for a long time. It was a mathematical equation that described the behavior of a wave. And what Schrodinger did is he actually took what we knew about the atom and plugged it in and got an equation for an atom. This right here represents the Schrodinger equation for an atom. You will not be responsible for anything to do with the Schrodinger model of the atom as far as math is concerned. You do need to know that this wave equation represents what's called the probability density. Okay, if you notice, this right here is what describes the atom, but it does not describe where an electron is. It describes the probability of it being in a certain location. That's why the Schrodinger model is often referred to as a quantum model of the atom, because it does not deal with an absolute position. Now, one of the interesting things about this is when you were to solve the 1s equation and the 2s equation and the 2p equation, these are the graphs that you would get for the probability density. So if you were to look right here, you get this peak right here, and there's your 2p, 3s, and so on. So you get these interesting patterns, and it's kind of tough to deal with these patterns because it looks in one dimension. You're just trying to look at it. But if you tried to take this graph and you tried to rotate it in 2 and then 3 dimensions, you'd come up with some familiar shapes. That's this. If you were to take the 1s orbital and you were to apply it, this is the shape you would get. This is the shape that corresponds to the graph. And what we talked about before in first year chemistry is that the s orbital is related to that shape. Whenever you take that same graph that we had for p, you would get that shape, which is the dumbbell shapes that we've talked about. So the probability densities, when you solve these Schrodinger equations, is the reason why we have these shapes of the orbitals. Okay, they're not just there because we think they're going to be that shape. It's actually solving the math out, and this is the probability function. Now, remember that whenever we talk about these shapes, the light part of the shape represents where the electron is 90% of the time. Okay, so that's a really key thing too. The electron could be somewhere else, but 90% of the time it's in that shape. So now we come to the idea of principal quantum numbers. Okay, there are four quantum numbers that define every electron in an atom. The first one is called the principal quantum number, and it's called n. What that refers to is the energy level of the electron. So they're labeled as KLMNOP. We generally don't look at them as KLMNOP. What we usually look at is 1, 2, 3, 4, 5, 6, 7, 8. What that means, these directly correspond to the periods on the periodic table. So you have a periodic table that looks like something like this. I'm doing a pretty poor job drawing it. But you have hydrogen and helium and then everything else below it. So you have periods. Everything in the first period has a principal quantum number of 1. Everything in the second one has a principal quantum number of 2, and 3, and 4, and 5, and 6, and so on. So its position on the periodic table as far as the rows, that determines the principal quantum number. Whenever you increase the quantum number, you're increasing the size of the orbital because you're extending it away from the nucleus. And that makes sense because that should make sense with what we've covered before. The second number that we're talking about is the quantum number L. Okay, so we've already defined n, and we said n could be 1, 2, 3, so on and so on and so on. The principal number quantum L depends on the quantum number L depends on the principal quantum number n. So if n is 1, there is only one possible value of L. L must equal 0. Okay, because L is determined by the equation n minus 1. So if n is 2, L can be 0 or 1. If n is 3, then L can be 0, 1, or 2. Now the interesting thing about this quantum number is this quantum number, often referred to as the angular momentum quantum number, that's not important, determines the shape of the orbital. If you have n is equal to 1 and L is equal to 0, the 0 says that I have an s orbital, and an s orbital is that one right there. Next, if you have n is equal to 2, L could be 0, which means there could be an s orbital, or L could be 1, which would mean that there's a p orbital. And if you were to look at next, we have the magnetic quantum number. The magnetic quantum number is called ML. So that's what we have here. And what it does is it actually describes the subshell or the arm that you're talking about for a particular orbital. So the ML value has these potential values. So for example, if L is 0, the only possible value of ML is 0. But if L is 1, the possible values would be -1, 0, and 1. And if L is 2, the possible values of ML would be -2, -1, 0, 1, and 2. So they represent the subshells or the arms of a particular orbital. So if you were to take a look at these, it makes sense that if you have an L shape of 0, remember, so if you have an L of 0, the shape is an s orbital. An s orbital is a sphere. The sphere has no arms or subshells or anything like that. But if you were to look at L equals 1, L equals 1 is a P shape. The P shape, we said, is a series of dumbbells. You have a dumbbell here, you have a dumbbell here, and it's hard to draw, but you have one coming into and out of the page. It's a three-dimensional structure. So you have 3 sets of dumbbells. So the ML1 actually determines the electron's orbital subshell. Now there is no difference between -1, 0, and 1. Okay, there's no difference in energy. What we tend to say though is there's X, Y, and Z. Okay, so we would say Px, Py, Pz. We can't do that with D because D actually has 5 orbital shells and there's not like an X, Y, Z, A, B dimensions. So we would say D -2, D -1, D0, D1, D2, and then you can do the same thing with F. So the interesting thing about these magnetic subshells is each one of them can hold 2 electrons. So if we're going to get into that in just a second, but if you were to look at it, since this one has no subshells, the s orbital can only hold 2 electrons. But this one has 3 orbitals, or 3 suborbitals. So because of that, each one of them can hold 2. You have 2 plus 2 plus 2, means that the p orbital can hold 6 electrons, which is exactly what you learned in the first year of chemistry. The d orbital has 5. 5 times 2 would be 10. And then the f orbital has 7. The f orbital has 7, then you would multiply it by 2, it's 14. Okay. You have your s orbital right here. It has a maximum of 2 electrons. It is a spherical shape, and remember, it's a 90% probability of finding the electron in that shape, and it represents the first 2 columns on the periodic table. So when you have this, it's the first 2 columns of the periodic table represent the s orbital. Next, you have the p orbital. It starts at the second energy level. So when you have that first row that has hydrogen and helium, you'll notice that there is no p orbital. Okay, no p orbital is possible in the first energy level, but it does start in the second one. In the second one, there's a maximum of 6 electrons. You can have 2 in px, 2 in py, 2 in pz. Once again, 90%. And it is group 13 through 18 on the periodic table. So if you were to look at the periodic table, you've got these 2 columns. And then it gets a little bit bigger over here. Okay, well, there's no something like that. These 6 elements right here, these 6 columns, represent the p orbital shapes. Next, you have the octet rule. Generally speaking, electrons like to have 8 valence electrons in the outer level. That means they have a full s and a full p orbital. Now, that's for elements 1 through 36, which tend to kind of get you to right there. When you start to get into these bigger electrons, that kind of falls apart, but we're not going to do that in this class. So for the most part, we like to say that something is stable if it has full s and full p valence orbitals. So now we have the d orbital. The d orbital starts on the 3rd energy level. Even though it looks like it's the 4th one on the periodic table, it's the 3rd energy level. It can hold a maximum of 10 electrons. It's got this D0, D1, all that kind of stuff. And it represents the transition metals on the periodic table. So when you have the periodic table, you've got your S, you've got your P. This middle section represents your d orbitals. Finally, you have your f orbital. It starts in the 4th energy level. It can hold a maximum of 14 electrons, and it is the lanthanides and lactanides. Lanthanides and actinides. Said that wrong. Okay, so you have these right here. You've got your S, you've got your P, you've got your D. The ones that are pulled out are the f orbitals. So the electrons spin in quantum numbers. Electrons themselves spin. Okay, they are charged. They're like the Earth, though, in the fact that they rotate themselves. Okay, so they can spin either way, clockwise or counterclockwise. Okay, that generally is referred to S or MS. Okay, it's seen both ways in books, but it's called the spin of an electron. Now, there are two possible values. We assign them as the +1/2 and the -1/2. And it actually doesn't matter. They don't say things like, oh, if it's spinning clockwise, it's +1/2, and counterclockwise, it's -1/2. It just makes no difference. We're just distinguishing between the two. The way that they figured this out, though, is if you have a magnetic field, one of the electrons will be attracted kind of towards the top, and the other one will be repelled towards the bottom based on the fact that they're spinning. Because a spinning electron is actually itself a magnet. So when you put a magnet in a magnetic field, well, if you put two north magnets together, they repel, they push away. And if you put a north and a south together, they attract. Now, the Pauli exclusion principle that